Good morning, I'm Jeeyun Kim, a co-first author of this paper. Today, I'll introduce our research DOGI to minimize write amplification in log structure systems. First, I present the motivation for our work. These days, log structure systems are widely used in various applications. By transforming many small-sized random updates to sequential append-only writes, log structure systems can achieve high write throughput. However, an append-only write can create a challenge. When a user updates existing data, the old block is invalidated and the new version is inserted into free space. And those invalid blocks remain on storage, occupying space. This invalid data is reclaimed through a process called garbage collection, GC. During GC, the system first copies valid blocks into free space and then erases the invalid blocks in bulk. Typically, the write amplification factor is used to quantify this GC overhead. So in this work, we focus on how to reduce WAP specifically through data placement techniques. As shown in this example, data placement techniques reduce WAP by predicting each block's invalidation time and grouping blocks with similar invalidation times. When a certain period elapses, the blocks in a group become invalid around the same time, avoiding any data copies. Many data placement techniques have been proposed so far. Among them, we focus on 4 SORA techniques, MIDAS, SEPBIT, PHFTL, and MLDT, and analyze them. These techniques follow a similar 3-step workflow. Step 1, when a user writes the data block, the technique predicts the block's invalidation time. Step 2, based on the predicted invalidation time, it assigns the block to one of several groups. Most blocks become invalid, but some may remain valid during GC due to misprediction. Finally, step 3, the technique decides the group to relocate them. So I'll explain the strategies that the 4 SORA techniques adopt across 3 steps. First, to predict the invalidation time of user-written blocks, techniques use 2 strategies. MIDAS and SEPBIT use a block's latest invalidation time for the prediction. After a block is written and later gets updated, they measure how long it takes for the old version to become invalid. The system then assumes the block will be updated again after a similar interval. Meanwhile, PHFTL and MLDT use on machine learning to improve prediction accuracy. Second, they separate user-written blocks by hardness. MIDAS, SEPBIT, and PHFTL use 2 groups, hard and cold, whereas MLDT uses 19 groups. Although the number of groups differs, all 4 techniques partition blocks into a fixed number of groups. Finally, for relocating GC-written blocks, most techniques use a block's age for relocation. If a block is copied for the first time, it is treated as having a short age and relocated to a warm group. If the block remains valid and is copied multiple times during GC, it is treated as old and relocated to colder groups over time. MLDT is different. It does not predict the remaining invalidation time of GC-written blocks. Instead, it assumes all GC-written blocks are cold and isolates them into a separate group. So far, we have analyzed 4 techniques, and this table summarizes their strategies. Then, this leads to a natural question about how close these techniques get to the optimum using these strategies. To analyze how close the existing techniques come to optimality, we designed a near optimal data placement technique, NoDaP. Since determining the optimal data placement is NP hard, many near optimal techniques have been proposed. NoDaP, however, is a new near optimal technique that we designed for our analysis across 3 steps we just discussed. For invalidation time prediction of both blocks, NoDaP uses exact knowledge with 100% accuracy. And for each workload, NoDaP finds the best group configuration that minimizes WAP offline and applies it. As a result, NoDaP achieves WAP close to 1, making it a useful reference baseline for comparison. With NoDaP as a baseline, we analyze SOTA techniques in more detail by evaluating 3 steps in isolation as shown in this checklist. First, we examine whether existing techniques can accurately predict the invalidation time of user-written blocks, comparing two approaches, heuristic-based prediction using the latest invalidation time and ML-based prediction with NoDaP. By measuring the prediction accuracy of each approach, we found that both are much less accurate than NoDaP. And poor accuracy increases WAP, resulting in about 2.5 times higher WAP than NoDaP. This result shows that existing techniques fail to predict accurately. Between the two, the ML-based approach provides higher accuracy and lower WAP. However, due to its computational overhead, the ML-based approach incurs about 6.5 times higher prediction latency than the heuristic-based approach. This result suggests that considering only prediction accuracy is insufficient, and that prediction latency also matters. Second, we evaluate whether existing techniques choose an appropriate group configuration to assign user-written blocks. We varied NoDaP and MLDT's number of groups, starting at 2 and increasing it gradually, and observed how WAP changes. With NoDaP, more groups split blocks more finely, so WAP keeps decreasing. For MLDT, however, WAP is minimized at 3 groups, but increases with more groups. This is because with only 2 groups, the coldest group ends up mixing warm and truly cold blocks. The warm blocks become invalid earlier, but occupy space, which increases WAP. However, when we increase the number of groups beyond 3, using too many groups makes invalidation time prediction harder, leading to more misassigned blocks and consequently, more valid blocks remain during GC. Existing techniques choose either too few groups or too many groups without considering these factors, and they fail to minimize WAP. Finally, we evaluate how existing techniques relocate GC-written blocks, focusing on age-based relocation. Age-based relocation moves blocks only in one direction toward colder groups. In contrast, GC-written blocks in NoDaP can be relocated to any group based on the remaining invalidation time. We measured WAP under age-based and under NoDaP's relocation policy. And we found that age-based relocation increases WAP by 19% compared with NoDaP, which indicates that existing techniques fail to relocate GC-written blocks to appropriate groups. Due to these 3 limitations, existing techniques exhibit higher WAP than NoDaP. As shown in the overall WAP results, the techniques show at least 2.5 times higher WAP than NoDaP. Therefore, we designed DOGI to address the limitations of existing techniques. DOGI has 3 design goals. First, DOGI aims to predict the invalidation time of user-written blocks accurately while keeping prediction latency low. To achieve this goal, we obtain a key insight from the following experiment. We evaluate the prediction accuracy across blocks with different invalidation times. The result shows that ML-based is more accurate for warm blocks, while the 2 methods achieve similar accuracy for the hottest and the coldest blocks. Based on this observation, DOGI uses fast heuristic-based prediction for the hottest and coldest blocks and an ML model for the remaining blocks. Second, DOGI selects and applies a group configuration that minimizes WAP. As we saw earlier, WAP is affected by the group configuration choice. To address this, DOGI predicts WAP for candidate group configurations and applies the one with the lowest predicted WAP. Third, to outperform age-based relocation, DOGI uses historical data to relocate GC-written blocks more appropriately. Then I'll explain a design overview of DOGI. When a block is written, first, a hot filter identifies the hottest blocks with the shortest invalidation time. The remaining non-hot blocks are then separated more finely by an ML model. DOGI determines its group configuration online using the ML model's prediction log. In each group, GC-written blocks that remain valid due to prediction errors are relocated to different groups. Then a frozen filter identifies the frozen blocks with the longest invalidation time. The remaining non-frozen blocks are separated by the prediction log. Now I'll explain each design component in more detail. DOGI uses a hybrid prediction method to estimate the invalid time of user-written blocks. First, user-written blocks pass through a hot filter, and hot blocks are filtered out separately. Since the hot filter relies on the latest invalidation time similar to CEPID and MIDAS, it provides low prediction latency. For the remaining non-hot blocks, DOGI uses the ML model. We adopt a multi-layered perceptron model, which we experimentally verified to be lightweight and accurate with 6 input features and 10 output categories. As a result, DOGI achieves low prediction latency with the hot filter, while also achieving high accuracy with an ML model trained to focus on remaining warm and cold blocks. Next, I'll explain how DOGI assigns user-written blocks in each group. There are many candidate group configurations with different number of groups, but we need to find the one that minimizes WAF. And as we saw earlier, minimizing WAF requires a configuration that can separate warm and cold blocks while keeping the misprediction penalty low. So DOGI predicts the WAF of group configurations by estimating the impact of these two factors. First, we use the ML model's prediction history for user-written blocks and compute the fraction of blocks assigned to each group. And we also look the actual invalidation times collected for model training. By comparing them with the predictions, we compute the misprediction rate. DOGI predicts the WAF of each group configuration by feeding these two metrics into a Markov chain model. So DOGI predicts WAF for candidate group configurations and applies the one that minimizes WAF. Finally, I'll explain DOGI's relocation policy for GC-written blocks. DOGI separates GC-written blocks in 2 stages, similar with user-written placement. First, DOGI uses a heuristic-based frozen filter to identify extremely cold blocks. And the remaining non-frozen blocks are relocated using the prediction log. DOGI identifies blocks whose prediction was incorrect. Among them, DOGI filters out blocks that were mispredicted as hotter. For these blocks, the actual invalidation time is longer than predicted, so they stay valid longer and take more time to become invalid. For these blocks, DOGI computes the remaining invalidation time using prediction log and assigns a GC category to each block based on the remaining invalidation time. DOGI then relocates GC-written blocks to the appropriate group using the GC category. So overall, DOGI is designed to address all 3 problems we observed in existing techniques. Due to time constraints, we could not cover all the details in this talk. The paper covers DOGI's detailed design, adaptation to changing I/O patterns, and overhead analysis. Please refer to the paper for details. Then I'll explain the evaluation of DOGI. We implemented DOGI prototype on ZNS SSD. And we evaluate DOGI under 6 workloads. For comparison, we implemented 4 SOTA techniques that we analyzed earlier in the motivation. First, we evaluate if DOGI effectively reduces WAF compared to other SOTA techniques. DOGI shows reduced WAF compared to other techniques. It achieves a 15% average WAF reduction compared to best performing baseline MIDAS. And it even outperforms other techniques on workloads with dynamic I/O patterns such as Farmail, Alibaba, and Exchange. Second, we analyzed the impact of the 3 individual design components of DOGI. Each component corresponds to an item in the checklist, and we denote them as user, group, and GC respectively. The results shows that group and GC reduce WAF by 15% and 22% over the baseline respectively. However, user increases WAF by 1%. This occurs because for some workloads, separating user-written blocks into too many groups amplifies the misprediction penalty and increases WAF. Once we apply group, increased WAF drops immediately. Finally, we analyze the throughput and prediction latency. DOGI shows higher throughput compared to SOTA techniques. It is because DOGI effectively reduces WAF without significant prediction overhead. To quantify the overhead of each technique's prediction policy, we also measure the average prediction latency. By DOGI's hybrid mechanism, DOGI achieves substantially lower latency than the ML-based PHFTL and comparable to the heuristic-based ZBit. Here is our conclusion. We identified 3 key problems in existing data placement techniques through a comparison with our near-optimal baseline NoDaP. Existing techniques often predict invalidation time inaccurately and fail to choose a group configuration that minimizes WAF. DOGI mitigates all these 3 problems, and our experiments showed that DOGI achieved lower WAF and higher throughput than prior techniques with low overhead. That concludes my presentation. Thank you.